Hello and welcome to the Sleepy Cosmos, where we journey through the universe's greatest mysteries with a gentle pace perfect for drifting off to peaceful sleep. Tonight, we'll explore the most groundbreaking discoveries from humanity's most powerful eye on the cosmos, the James Webb Space Telescope, as we float together through the infinite beauty of deep space. Imagine now that we're travelling together through the cosmic dark, leaving behind the familiar lights of Earth to reach a place unlike anywhere else in our solar system. We're drifting toward Lagrange Point 2, a gravitational sweet spot 1 million miles away, where the combined pull of Earth and Sun creates a perfect balance. Here, in this quiet corner of space, hovers our destination, a golden mirror larger than a tennis court, unfolded like a metallic flower against the star-filled void. As you float beside this marvel of human engineering, take a moment to appreciate where we are. We're so far from Earth that our beautiful blue planet appears as nothing more than a pale dot, smaller than a pinhead held at arm's length. The moon is just another tiny speck of light in the distance. We've travelled beyond the gravitational embrace that holds our world together to a place where we can see the universe without interference. This is the perfect cosmic observatory, a quiet harbour in the sea of space where we can listen to the whispers of distant worlds and ancient light. Here, James Webb can observe the cosmos in perfect darkness, never blinded by sunlight or disturbed by our planet's warm glow. The telescope itself is a wonder to behold. Its primary mirror, made of 18 hexagonal segments of gold-plated beryllium, stretches 21 feet across, nearly 3 times larger than Hubble's mirror. Each segment was polished to perfection, smoother than anything humans had created. When starlight catches these golden mirrors, they gleam like a technological flower blooming in space. Behind the mirrors, a tennis court-sized sunshield unfolds like metallic butterfly wings, protecting the delicate instruments from the sun's heat and light. This shield is so effective that the sun-facing side reaches temperatures over 200 degrees Fahrenheit, while the observatory side stays at -370 degrees Fahrenheit, colder than Pluto. This extreme cold is essential because James Webb sees in infrared light, and any warmth would blind its detectors. But we're not here just to admire this technological marvel. We're here because this telescope has fundamentally changed our understanding of the universe in ways that would have been fantasy years ago. Since beginning its cosmic vigil, James Webb has sent back images and data that have rewritten textbooks and revealed a universe far stranger and more beautiful than we imagined. As you drift in the peaceful silence of space, surrounded by the gentle glow of starlight from billions of distant suns, prepare yourself for a journey unlike any taken before. We're about to travel not just through space, but through time itself. The light that James Webb captures has been travelling toward us for billions of years, carrying messages from the ancient universe when galaxies were young. James Webb sees in infrared light, which allows it to peer through cosmic dust clouds that would block visible light completely. This means it can observe the birth of stars and planets, watch galaxies form in the early universe, and analyse distant atmospheres, all previously impossible. It's like suddenly being able to see through walls after wondering what lies beyond. Perhaps most remarkably, this telescope allows us to look backward through time. Because light takes time to travel across vast distances, the farther away we look, the further back in time we see. When James Webb observes a galaxy 12 billion light years away, it's seeing that galaxy as it existed 12 billion years ago, when the universe was young. We can literally observe the universe growing up. We can watch as the first stars ignite in primordial galaxies, see how cosmic structures formed and evolved, and trace star formation history across cosmic time. It's like having a time machine that allows us to witness the universe's childhood and maturation. As we prepare to begin this cosmic journey together, let yourself feel the profound peace that comes from contemplating these vast scales of space and time. The universe is so much larger and older than our daily concerns, so much more beautiful and mysterious than we could comprehend. There's something deeply comforting about placing ourselves within this cosmic context. Tonight, as James Webb's discoveries unfold before us like a cosmic bedtime story, let this knowledge settle into your consciousness like starlight falling gently through space. The telescope floating beside us represents humanity at its best, our curiosity, ingenuity, and desire to understand our place in the cosmos. If this gentle voyage through space and time brings you peace, if these revelations help quiet daily worries, a soft like or subscribe helps these stories reach souls seeking connection to something larger than themselves. So settle back now into the vast, peaceful silence of space, 1 million miles from Earth. Feel the gentle gravitational currents that hold James Webb in perfect position, and prepare to see the universe through the most powerful eyes humanity has created. As we settle into our cosmic vantage point alongside James Webb, prepare to witness something that defies comprehension and challenges everything we thought we knew about the universe's infancy. We're about to look backward through time itself, watching the universe when it was just a child, barely 400 million years old. The light reaching us now has been travelling for over 13 billion years, carrying images of galaxies as they existed when the cosmos was young, wild, and fundamentally different from the ordered universe we inhabit today. This is James Webb's greatest superpower. Its ability to see in infrared light allows it to detect the stretched, reddened light from the most distant objects in the observable universe. As space itself expands, it stretches the wavelengths of light travelling through it, shifting what was once brilliant visible light into infrared radiation that only James Webb's sensitive instruments can detect. We're essentially looking at baby pictures of the universe, snapshots taken when everything we know was just beginning to take shape from the primordial cosmic soup. The first galaxies James Webb discovered in the infant cosmos shocked astronomers around the world and forced them to reconsider fundamental assumptions about cosmic evolution. These primeval galaxies appear far more massive, organised, and mature than anyone expected based on our most sophisticated computer models. According to our best theories, developed over decades of careful observation, these cosmic infants should have been small, chaotic collections of stars, cosmic teenagers still figuring out their identity. Instead, James Webb revealed galaxies that seem surprisingly grown up for their age, challenging everything we thought we knew about how quickly the universe could evolve from simplicity to complexity. One of the most remarkable discoveries is galaxy GNZ 13, which existed when the universe was only 400 million years old, a cosmic toddler by any measure. To put this in perspective, if the entire 13.8 billion year history of the universe were compressed into a single year, this galaxy would have formed in early February, when the cosmos was still in its infancy, and most of what we consider normal hadn't yet come into existence. Yet this galaxy contains billions of stars and shows signs of sophisticated structure that astronomers didn't expect to see for billions of years later in cosmic history. The light from these primeval galaxies tells us stories that read like cosmic fairy tales, written in the language of physics and chemistry. We can see galaxies in the process of merging, their gravitational dance creating spectacular streams of stars that stretch across millions of light years like celestial ribbons. These cosmic collisions were common in the infant cosmos, as smaller proto-galaxies collided and combined in a profound choreography to form the larger, more stable structures we see dominating the modern cosmos today. Through Webb's eyes, astronomers have glimpsed that star formation in the infant cosmos happened at a frenzied pace that dwarfs anything we see in the modern cosmos, where star birth has slowed to a more leisurely rate. These primordial galaxies were star-making factories operating at maximum capacity, converting gas and dust into new suns at rates hundreds of times faster than typical galaxies today. It was as if the universe was in a hurry to light itself up, rushing to fill the infinite darkness with the warm, life-giving glow of stellar light that would eventually make planets and life possible. The colours in these primeval galaxies are unlike anything in our modern universe, painted in hues that no longer exist in today's mature cosmic landscape. Early stars were predominantly massive, hot and blazing blue, burning through their nuclear fuel at prodigious rates that would consume our sun's entire lifetime supply in just a few million years. These stellar giants lived fast and died young, exploding as profound supernovas that scattered the first heavy elements throughout space like cosmic seeds. The light from these ancient stellar populations appears shifted toward deep red in James Webb's images, but we know these were actually blazing blue-white furnaces that illuminated the cosmic dawn with unique brilliance. Perhaps most mysteriously, astronomers using Webb have uncovered galaxies that seem impossibly large and bright for their tender age, defying our understanding of how cosmic structures grow and evolve. Some of these early galaxies appear to contain supermassive black holes that somehow grew to enormous sizes much faster than our current theories predict should be possible. It's like finding fully grown oak trees in a forest that was planted yesterday. These discoveries are forcing astronomers to completely rethink how quickly cosmic structures can form, evolve, and mature in the universe's earliest epochs. The universe during this early period was a very different place from the stable, organised cosmos we inhabit today. Space was smaller, denser, and significantly hotter than it is now. Galaxies were packed more closely together, making violent collisions and dramatic interactions much more common than in our modern, more spacious universe. The cosmic web of dark matter that provides the invisible scaffolding for galaxy formation was still under construction, creating a more chaotic and dynamic environment than we see in the present day. James Webb's observations have revealed that these early galaxies existed during a crucial time called the Epoch of Ionization, when the first stars and galaxies began to shine brightly enough to ionize the hydrogen gas that filled the universe like a thick cosmic fog. Before this transformative time, the cosmos was dark and filled with neutral hydrogen that absorbed most light, making the universe opaque to radiation. The first galaxies acted like cosmic lighthouses, gradually clearing the primordial fog and making the universe transparent to light for the first time since the Big Bang's initial flash. This period represents one of the most dramatic transformations in cosmic history, when the universe literally changed from a dark, opaque realm into the transparent cosmos we see today. The process took hundreds of millions of years, with each new generation of stars contributing to the gradual ionization of intergalactic space. It was like watching the universe slowly wake up from a deep sleep, opening its eyes to light for the first time. The telescope's incredible sensitivity allows us to study not just the brightest early galaxies, but also the faint, smaller ones that populated the ancient universe in vast numbers. These dim galaxies are actually more representative of typical galaxy formation in the early cosmos, and they provide crucial clues about how the universe evolved from its initial state of nearly perfect simplicity to the rich, complex structure we see today, filled with countless galaxies, stars, and worlds. One of the most profound realizations from James Webb's infant cosmos observations is that we are literally seeing our own cosmic ancestry playing out in the distant past. The elements that make up our bodies, the carbon in our cells, the oxygen we breathe, the iron flowing through our blood, were forged in the nuclear furnaces of these very ancient stars we're observing. When these massive early stars exploded as supernovas, they scattered these precious elements throughout space, eventually incorporating them into later generations of stars, planets, and ultimately, the complex chemistry that makes life itself possible. The process of cosmic chemical evolution that James Webb observes in these early galaxies is the foundation story of everything we know and love. Each supernova explosion enriched the universe with heavier elements, gradually building up the chemical complexity necessary for rocky planets and biological life. We are witnessing the universe learning how to make the ingredients for complexity, beauty, and consciousness, watching the cosmos develop the tools it would need to eventually create beings capable of looking back and understanding their own origins. This cosmic evolution follows a pattern of increasing complexity that mirrors the development of life itself. Simple hydrogen and helium gradually gave way to heavier elements, which enabled the formation of dust grains, then rocky planets, and eventually the sophisticated chemistry required for biological molecules. Each step built upon the previous one, creating an unbroken chain of complexity that connects the first stars to the neurons firing in our brains as we contemplate these ancient images. James Webb's images of the infant cosmos possess an ethereal, dreamlike quality that seems almost too beautiful to be real, like paintings created by some cosmic artist working with light itself. The galaxies appear as delicate spirals and ellipses suspended in the infinite cosmic dark, their ancient light red-shifted into warm oranges and deep reds that glow like precious embers in a dying fire. Yet these are not dying embers, but cosmic nurseries blazing with the light of billions of newborn stars, each one a sun that might warm planets we can barely imagine. The distance scales involved in these observations boggle the human mind and stretch our capacity for wonder to its limits. When we look at a galaxy 13 billion light-years away, we're seeing light that has been travelling toward us for most of the universe's entire existence. This light began its journey when the cosmos was fundamentally different from today, and it has witnessed the entire grand evolution of the universe during its incredibly long voyage to reach our telescopes here at this quiet outpost of space. As we contemplate these primeval galaxies floating in the peaceful darkness around us, we can sense the profound continuity that connects us to these distant times and places across the vast gulf of space and time. The same physical laws that governed these early galaxies continue to operate in our modern cosmos. The same nuclear processes that powered their brilliant stars continue to fuel our own sun. The same gravitational forces that shape their evolution continue to influence the graceful motion of our Milky Way galaxy through space today. James Webb's revelations about the infant cosmos remind us that we exist within an unbroken chain of cosmic evolution stretching back to the very beginning of time itself. Every atom in our bodies was once part of these ancient stellar furnaces, and every breath we take connects us to the cosmic processes that began over 13 billion years ago in those first moments after the Big Bang. The beauty of these discoveries lies not just in their profound scientific importance, but in their ability to inspire wonder and place our existence within the grandest possible context imaginable. We are not separate observers of the cosmos we study. We are the universe becoming conscious of its own profound history, matter organized in such a way that it can contemplate its own origins and evolution with awe and understanding. In looking back at these primeval galaxies, we are literally seeing the universe looking at itself through our eyes. Now we turn our cosmic gaze toward one of the universe's most beautiful and fundamental processes, the birth of stars. Through James Webb's revolutionary infrared vision, we can peer into stellar nurseries that have remained hidden from human eyes for all of history, watching as gravity and physics collaborate in an ancient dance to create the cosmic furnaces that light up the darkness and make life itself possible. Imagine drifting through the vast emptiness of space toward a region that appears utterly barren to the naked eye, just a dark patch against the star-filled sky like an empty canvas waiting for creation. But as James Webb's infrared sensors engage and begin their patient observation, this apparent emptiness transforms into something truly profound and alive. Vast clouds of gas and dust, larger than the entire solar systems and containing enough material to form thousands of stars, begin to glow with hidden warmth that speaks of cosmic processes beyond imagination. These are stellar nurseries, cosmic wombs where new stars are born in processes that stretch across millions of years, each birth a testament to the universe's infinite patience and creativity. The scale of these star-forming regions defies comprehension. Some molecular clouds stretch for hundreds of light years and contain enough material to create entire stellar neighborhoods that will shine for billions of years. The Eagle Nebula, one of James Webb's most spectacular and scientifically valuable targets, reveal star formation in unique detail that takes the breath away. What appears as towering pillars of cosmic dust stretching across light years are actually stellar maternity wards, where gravity slowly and methodically gathers material together until it reaches the critical mass needed to ignite nuclear fusion. These pillars stretch for incredible distances, each one a profound monument to the patient, inexorable work of cosmic creation that has been ongoing since the universe first began forming stars. Within these dusty columns that rise like cosmic mountains, James Webb can see through the opaque veils that have hidden starbirth from all previous telescopes throughout human history. The infrared light reveals protostars, stellar embryos still actively gathering mass from their surrounding cocoons of dust and gas, growing larger and denser with each passing century. These baby stars glow with the gentle heat of gravitational collapse, slowly warming as they accumulate more material, preparing for that momentous occasion when they will finally ignite and join the cosmic community of shining suns that illuminate the universe. The entire process begins with the gentlest of disturbances in these vast molecular clouds that drift through space like cosmic phantoms. Perhaps a nearby supernova sends a powerful shockwave rippling through the region, compressing the gas and triggering collapse. Or the gravitational influence of a passing star compresses the material just enough to tip the delicate balance. Sometimes the spiral arms of our galaxy create density waves that squeeze the clouds as they pass through. Whatever the initial trigger might be, gravity begins its patient, relentless work, pulling material together grain by grain, molecule by molecule, over timescales that absolutely dwarf the entirety of human civilization. As the cloud contracts under its own weight, it begins to spin faster and faster, following the same physical principles that govern a figure skater, pulling in their arms during a graceful pirouette. This rotation gradually flattens the collapsing material into a disc-like structure, with the forming star taking shape at the center, surrounded by a swirling pancake of gas and dust that will eventually provide the raw material for planets. James Webb can observe these protoplanetary disks in exquisite detail, watching the very process that formed our own solar system roughly 4.5 billion years ago. Temperature and pressure rise steadily and relentlessly in the center of the collapsing cloud as gravitational forces compress the material to ever-increasing densities. What started as a diffuse collection of molecules spread across light years becomes increasingly concentrated and hot, the stellar embryo growing denser and warmer with each passing millennium. The temperature climbs steadily from the frigid cold of interstellar space, nearly absolute zero, to hundreds, then thousands of degrees as gravitational potential energy converts to thermal heat energy. The moment of stellar ignition represents both a gradual process and a sudden transformation that changes everything. For millions of years, the protostar has been warming slowly and steadily, building toward a critical threshold. Nuclear fusion requires incredibly precise conditions, a core temperature of approximately 10 million degrees Celsius and pressures millions of times greater than Earth's atmosphere. When this critical threshold is finally reached, after eons of patient waiting, hydrogen nuclei begin fusing into helium nuclei, and a new star is born in a blaze of nuclear glory. The gentle glow of gravitational heating suddenly gives way to the brilliant sustained fire of nuclear fusion that will burn for billions of years. This moment transforms the protostar from a warm, glowing ember into a genuine star, a nuclear furnace that will spend the rest of its life converting hydrogen into heavier elements and radiating energy into space. James Webb captures this profound process at various evolutionary stages throughout different star-forming regions across our galaxy and beyond. In the spectacular Carina Nebula, we can observe stars that have just recently ignited their nuclear engines, still surrounded by the dusty cocoons of their birth like cosmic butterflies, not yet emerged from their chrysalises. Their intense radiation and powerful stellar winds are beginning to blow away the remaining gas and dust, gradually revealing the newborn stars in all their nuclear-powered glory. The diversity of stellar birth throughout the universe is truly remarkable and speaks to the richness of cosmic processes. Massive stars, dozens of times more massive than our Sun, form relatively quickly in cosmic terms and burn bright and hot with nuclear fires far more intense than our own star. These stellar giants live fast-paced lives that end in spectacular supernova explosions after just a few million years. Brief candles in cosmic time that reshape their entire neighborhoods through their fierce radiation and final explosive deaths. Smaller stars like our Sun form more gradually and burn their nuclear fuel at a much more measured, sustainable pace, allowing them to shine steadily and reliably for billions of years. These long-lived stars provide the stable environment absolutely necessary for planets to form and cool, and for life to evolve over the vast timescales required for biological complexity. James Webb can observe both types of stellar formation, from the dramatic, rapid birth of massive giants that burn bright and die young, to the quiet, gradual emergence of sun-like stars that will shine for geological ages. The telescope reveals intricate, beautiful structures within star-forming regions that were completely invisible to previous instruments, no matter how sophisticated. We can see bow shocks where powerful stellar winds collide with surrounding material, creating graceful, curved formations that look like cosmic works of art painted with light and gas. We observe jets of material streaming away from young stars at tremendous speeds, sometimes thousands of kilometers per second, providing clear evidence of the violent and dynamic processes involved in stellar birth. One of James Webb's most remarkable and scientifically valuable capabilities is its unique ability to see through the thick, obscuring dust that surrounds forming stars like cosmic fog. Earlier telescopes could only observe the outer edges of stellar nurseries, seeing only the surfaces of these cosmic clouds. But infrared light passes through cosmic dust like sunlight through morning mist, allowing us to peer deep into the hearts of these regions and watch stars being born in what amounts to real time for astronomical processes. The colours in James Webb star formation images tell detailed stories of temperature, chemical composition, and evolutionary stage that astronomers can read like a cosmic book. The coolest dust glows in deep red infrared light, indicating temperatures just barely above absolute zero. Warmer regions appear in oranges and yellows, while the hottest areas shine in brilliant whites and blues. Newly formed stars blaze with brilliant white light, their nuclear furnaces finally ignited after millions of years of patient gravitational collapse and heating. These stellar nurseries serve as planetary system factories as well as star-forming regions, containing all the raw materials and conditions needed to build entire solar systems. The disks of material surrounding young stars contain all the ingredients needed to construct planets: rocky materials and metals for terrestrial worlds close to the star, and ices, gases, and organic compounds for giant planets in the colder outer regions. James Webb can observe these protoplanetary disks directly, watching the early stages of planet formation as microscopic dust grains stick together electrostatically to form larger and larger objects. The telescope has revealed that planet formation begins much earlier in the stellar formation process than astronomers previously expected or theorized. Even very young protostars, still surrounded by thick envelopes of dust and gas and not yet fully ignited, already show clear signs of planetary system formation in their circumstellar disks. This discovery suggests that planets may be a common, perhaps even inevitable outcome of star formation, potentially making worlds like Earth far more abundant throughout the universe than we previously dared to imagine. Star formation rarely occurs as a solitary process in the cosmic void. Young stars typically form in clusters, groups of hundreds or thousands of stellar siblings born from the same parent giant molecular cloud over relatively short periods of cosmic time. These stellar nurseries are bustling neighborhoods where newborn stars interact with each other through gravitational influences and radiation pressure, mutually influencing each other's development, evolution, and ultimate fate in complex ways. James Webb's groundbreaking observations reveal that star formation is an ongoing, continuous process throughout the universe, not just an ancient phenomenon from the cosmos's youth. Even in our own Milky Way galaxy, new stars are being born at a steady rate of approximately one per year, maintaining the galaxy's stellar population and continuing the cosmic cycle of stellar birth, life, and death that has persisted for over 10 billion years. As we observe these stellar birthplaces through James Webb's unique infrared eyes, we witness the universe engaged in its most fundamental and important creative act. Every star that has ever shone throughout cosmic history, including our own life-giving sun, began its existence in such a nursery. The process we observe happening now in distant nebulae across the galaxy is precisely the same process that created the star that warms our planet, drives our weather systems, and makes all life on Earth possible through photosynthesis and solar energy. The profound beauty of these stellar nurseries lies not just in their remarkable visual splendor, but in their crucial role as cosmic recycling centers that process and reprocess the chemical elements of the universe. The gas and dust in these regions come from previous generations of stars that lived out their entire life cycles and returned their enriched material to space through stellar winds and explosive supernova deaths. This recycled material, now enriched with heavy elements like carbon, oxygen, silicon, and iron that were created in stellar nuclear cores, becomes the essential building blocks for new stars and the planetary systems that orbit them. Each newborn star carries within its planets and their potential for life the complete chemical legacy of all the stars that came before it in cosmic history. The carbon that forms the backbone of every organic molecule in our bodies, the oxygen that we breathe with every inhalation, the silicon that makes up the rocks beneath our feet, all were created in the nuclear furnaces of ancient stars and recycled through stellar nurseries exactly like those that James Webb observes throughout the universe today. In this endless cycle of stellar birth, death, and rebirth, we find our own cosmic story written in the language of physics and chemistry. Every breath we take connects us to these stellar nurseries, every heartbeat echoes the nuclear rhythms of distant suns, and every thought arises from atoms seeded by stellar fires that died billions of years ago, connecting us eternally to the cosmic story of creation and renewal. Our cosmic journey continues as we drift alongside James Webb toward perhaps the most profound question in all of science. Are we alone in the universe? Through this telescope's unique ability to analyze the atmospheres of distant worlds, we're beginning to answer questions that have puzzled humanity since we first looked up at the stars and wondered if other Earths might exist among the countless points of light scattered across the night sky. Imagine travelling with us now toward distant star systems, some hundreds of light years away, where alien worlds orbit foreign suns in gravitational dances we're only beginning to understand. These exoplanets, planets beyond our solar system, were mere theoretical possibilities just a few decades ago, subjects of science fiction rather than scientific fact. Today, James Webb can not only detect these distant worlds with remarkable precision, but actually analyse their atmospheres in unique detail, telling us what gases surround them, what their weather systems might be like, and whether they might harbour the precious conditions necessary for life as we know it, or even as we don't yet know it. The telescope's atmospheric analysis works through a beautiful and elegant process called transit spectroscopy, which sounds complex but operates on principles as simple and fundamental as looking at shadows and light. When an exoplanet passes in front of its host star as seen from our perspective on Earth, an event astronomers call a transit, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us across the vast distances of interstellar space. Different gases in that alien atmosphere absorb specific wavelengths of light, creating a unique chemical fingerprint that James Webb can read with remarkable precision and sensitivity. This remarkable process is like analysing the ingredients of a distant soup by studying the light that passes through it. Each type of molecule, water vapour, carbon dioxide, methane, oxygen, nitrogen, leaves its own distinctive signature in the light spectrum, allowing astronomers to determine not just what gases are present in these alien atmospheres, but in what quantities they exist, at what temperatures and pressures, and how they might interact with each other to create complex atmospheric chemistry. One of James Webb's most remarkable and scientifically significant discoveries involves WSP-96b, a puffy hot Jupiter orbiting a star 1,150 light-years away in the southern constellation Phoenix. When this massive planet transits its star, James Webb detected clear and unambiguous evidence of water vapor in its atmosphere. Actual H2O molecules, the same precious substance that fills our oceans, flows through our rivers and makes up most of our bodies, existing on a world so distant that its light takes over a millennium to reach us through the cosmic void. But water vapor represents just the beginning of James Webb's atmospheric revelations about the diversity of alien worlds. The telescope has detected exotic clouds made of tiny silicate particles, essentially microscopic droplets of molten glass, floating in the atmospheres of distant worlds like alien precipitation. These remarkable clouds drift through skies that might glow with colours we've never seen on Earth, under the light of stars very different from our Sun, creating weather patterns and atmospheric dynamics that operate according to the same fundamental physical laws, but under conditions so extreme they challenge our imagination and expand our understanding of what's possible in planetary science. The telescope has revealed atmospheric compositions that challenge and dramatically expand our understanding of planetary formation and evolution throughout the galaxy. Some exoplanets show evidence of atmospheres rich in carbon monoxide, methane, ammonia, hydrogen sulfide, and other molecules that paint pictures of alien weather systems operating under physical and chemical conditions we're only beginning to understand. These discoveries force us to expand our definitions of what constitutes a planetary atmosphere and how such complex systems can develop, evolve, and persist over billions of years under different stellar and gravitational influences. Perhaps most intriguingly for the search for life beyond Earth, James Webb has begun to analyse the atmospheres of rocky planets similar in size and mass to our own world. These terrestrial exoplanets orbit in their star's habitable zone, that special distance where liquid water could potentially exist on the surface without freezing solid or boiling away into space. The telescope's detailed analysis of these Earth-like worlds represents our first real opportunity to search systematically for biosignatures, chemical evidence of life in distant atmospheres that might reveal we are not alone. The process of atmospheric analysis requires incredible precision and technological sophistication that pushes the absolute boundaries of what's possible with current scientific instruments. The amount of starlight that filters through an exoplanet's atmosphere during a transit is vanishingly small, like trying to detect the shadow of a fruit fly passing in front of a lighthouse beam from many miles away, or measuring the dimming of a car's headlight when a moth flies across it. Yet James Webb's instruments are so sensitive and precisely calibrated, they can measure these tiny variations in light intensity and extract detailed information about atmospheric composition, temperature gradients, and pressure systems. Each atmospheric spectrum that James Webb captures tells a detailed and complex story about the world it came from, like reading a chemical autobiography written in the language of light and physics. High concentrations of water vapor might indicate abundant oceans covering most of the planet's surface, or thick cloud cover similar to Venus's perpetual shroud. The presence of free oxygen could suggest photosynthetic life processes similar to those that transformed Earth's atmosphere, while significant methane concentrations might indicate either active geological processes like volcanism or biological activity producing organic compounds. Carbon dioxide levels can reveal crucial information about a planet's climate system, greenhouse effect, and potential for maintaining liquid water on its surface. The telescope has discovered atmospheres unlike anything in our own solar system, dramatically expanding our understanding of what's possible in planetary science and atmospheric dynamics. Some exoplanets have atmospheres made primarily of hydrogen and helium, like miniature versions of Jupiter, but orbiting much closer to their host stars, where temperatures reach thousands of degrees. Others show evidence of atmospheres dominated by heavier molecules like water vapor, carbon dioxide, or even more exotic compounds, creating dense, alien environments where the fundamental laws of chemistry and physics play out under conditions so extreme and unfamiliar they challenge our theoretical models and force us to develop new frameworks for understanding planetary atmospheres. James Webb's observations have revealed that atmospheric loss is a common and critically important phenomenon among exoplanets throughout our galaxy and beyond. Many worlds, particularly those orbiting close to their host stars, show clear and measurable evidence of their atmospheres being slowly but steadily stripped away by intense stellar radiation, powerful stellar winds, and high-energy particle bombardment. This atmospheric erosion process, operating over millions and billions of years, helps explain why some planets successfully retain thick, protective atmospheres that can support stable climates, while others become barren, airless rocks despite initially forming with substantial gaseous envelopes. The incredible diversity of exoplanet atmospheres tells us profound and detailed stories about the vast variety of planetary formation processes throughout the universe. Some worlds formed close to their stars in the hot inner regions of their protoplanetary disks, and later migrated inward through gravitational interactions with other planets, or the disk material itself. Others formed in the cold outer regions where water freezes solid, and were later heated by stellar evolution, gravitational compression, or orbital migration. Each unique formation history leaves its distinctive signature in atmospheric composition and structure, creating a vast library of planetary stories we're only beginning to read and understand. One of the most exciting and potentially revolutionary aspects of James Webb's exoplanet research is its growing ability to study potentially habitable worlds with increasing precision and sensitivity. The telescope can detect biosignatures, atmospheric gases that might be produced by living organisms engaged in metabolic processes. Free oxygen combined with water vapor could indicate photosynthetic life processes similar to those that transformed Earth's atmosphere billions of years ago. More exotic biosignatures like phosphine, ammonia, or even more unusual compounds might suggest biological processes unlike anything on Earth, dramatically expanding our understanding of how life might manifest under different planetary conditions. The telescope's remarkable sensitivity allows it to study not just giant gas planets that are relatively easy to detect due to their size, but increasingly smaller rocky worlds more similar to Earth in size, mass, and composition. These terrestrial exoplanets are much more challenging to study because they produce weaker atmospheric signals and require longer observation times, but they represent our best hope for finding worlds that might harbour life as we understand it, or perhaps entirely new forms of life we haven't yet imagined. James Webb has detected complex and dynamic weather patterns on distant worlds, including sophisticated cloud formation systems, global wind patterns, and temperature variations that create dynamic, ever-changing atmospheric conditions. Some exoplanets show evidence of global atmospheric circulation that efficiently transports heat from their permanently daylit sides to their eternal night sides, while others appear to have more complex circulation patterns driven by seasonal changes, unusual orbital characteristics, or interactions with multiple star systems. As we study these distant atmospheres through James Webb's extraordinarily sensitive instruments, we gain entirely new perspective on our own planet's precious and utterly unique atmosphere. Earth's atmospheric composition represents a delicate balance of gases that took billions of years to evolve to its current life-supporting state through complex interactions between geological processes, biological evolution, and astronomical influences. The oxygen we breathe was largely produced by photosynthetic organisms over vast geological timescales, while the carbon dioxide that plants require has been regulated by intricate feedback systems involving weathering, volcanism, and life itself. The search for life through atmospheric analysis represents one of humanity's greatest and most ambitious scientific endeavours, combining cutting-edge technology with profound philosophical questions about our place in the universe. Each detailed spectrum that James Webb captures from a distant world brings us measurably closer to answering the fundamental question of whether life exists elsewhere in the cosmos, and whether we are truly alone among the stars or part of a vast community of living worlds connected by the same physical laws and chemical processes. James Webb's exoplanet discoveries remind us that planets are remarkably common throughout the universe, with most stars hosting at least one world and many hosting entire families of planets with diverse characteristics. This realization suggests that the universe may be filled with worlds of incredible diversity and beauty, each one representing a unique experiment in how matter and energy can organize themselves under different gravitational, thermal, and chemical conditions to create the complex systems we call planets. In the gentle silence of space as we float alongside this profound telescope, we continue our patient search for atmospheric signatures that might reveal we are not alone. Each new discovery adds another chapter to the growing story of planetary diversity, bringing us closer to understanding our place in the cosmic community of worlds that fills the universe with beauty, complexity, and perhaps life itself. Our journey through cosmic time continues as we drift deeper into the universe's greatest mysteries alongside the silent sentinel of James Webb. We're about to witness how the cosmos organized itself from nearly perfect simplicity into the profound structures we see today. Through James Webb's revolutionary infrared eyes, we can observe the universe learning to build galaxies, vast cities of stars that serve as the fundamental architecture of the cosmos and the stage upon which all cosmic drama has unfolded for billions of years. Imagine floating backward through time to an era when the universe was young, smooth, and almost entirely featureless. Just a few 100 million years after the Big Bang, space was filled with a nearly uniform soup of hydrogen and helium gas, the simplest and most abundant elements in existence. There were no stars yet blazing in the darkness, no galaxies spiraling through space, no complex structures of any kind, just gentle ripples in the cosmic fabric, tiny variations in density that would eventually grow into the profound galaxies we see scattered throughout the universe today, like islands of light in an infinite ocean. These primordial ripples were incredibly small, density variations of just 1 part in 100,000, fluctuations so subtle they would be nearly impossible to detect without the most sensitive instruments ever conceived. To put this in perspective, imagine a perfectly smooth lake stretching to every horizon with waves only a few millimeters high, barely disturbing its mirror-like surface. Yet from these tiny ripples in the cosmic ocean, gravity would eventually sculpt galaxies containing hundreds of billions of stars, each galaxy a universe unto itself filled with countless worlds, infinite possibilities, and perhaps even life. James Webb can observe this profound process in action by looking at galaxies at different distances and therefore different ages, essentially creating a time-lapse movie of cosmic evolution spanning billions of years. The telescope reveals a universe in the very act of organizing itself, showing us galaxies at various stages of formation and evolution, like snapshots from a cosmic photo album that chronicles the transformation from chaos to order. We can literally watch cosmic structure emerge from primordial simplicity, order arising from randomness through the patient work of physical laws operating across timescales that dwarf human comprehension. The earliest galaxies James Webb observes appear small and irregular, more like scattered collections of bright star clusters than the grand spiral and elliptical galaxies we see in our local cosmic neighborhood. These primordial galaxies were still learning how to be galaxies, experimenting with different ways to organize their stars and gas, testing various configurations and structures as they slowly grew larger and more complex through mergers and the continuous accretion of surrounding material from the cosmic web. Dark matter plays a crucial and invisible role in this cosmic construction project, providing the hidden gravitational foundation upon which all visible structure is built. Though completely invisible to our eyes, and even to James Webb's extraordinarily sensitive instruments, Dark matter provides the gravitational scaffolding that guides and controls galaxy formation throughout the universe. James Webb's observations confirm that galaxies form within vast, invisible halos of dark matter, like profound cities built on foundations we cannot see, but which determine the shape, stability, and ultimate fate of everything visible above. The process of galaxy formation involves countless collisions and mergers, a cosmic dance of gravity that spans billions of years and involves galaxies of all sizes and masses. Small proto-galaxies combine to form larger ones in a hierarchical process that builds complexity from simplicity, structure from randomness. James Webb can observe these mergers in progress, watching as galaxies distort each other's shapes through powerful gravitational interactions and eventually combine into single, larger systems that inherit the combined mass, stars, stellar populations, and evolutionary history of their predecessors. One of James Webb's most surprising and scientifically challenging discoveries is how quickly some early galaxies achieved impressive sizes and masses that rival even the most massive galaxies in our modern universe. These primeval galaxies appear more mature, organised, and massive than our most sophisticated computer models predicted they should be at such early cosmic ages, suggesting that galaxy formation could happen much faster than we previously understood. This discovery is forcing astronomers to completely revise fundamental theories about how cosmic structure emerges from the smooth, infant cosmos. The telescope reveals that galaxy formation is intimately connected to star formation in complex feedback loops that operate across cosmic time. As gas collapses under gravity to form the first generation of stars, those newly born stars begin to heat and ionize the surrounding material through their intense radiation and powerful stellar winds, fundamentally affecting how subsequent generations of stars can form, where they can form, and at what rates. This intricate feedback between star formation and galaxy evolution creates complex, interconnected processes that determine the ultimate character of each galaxy. Supermassive black holes also play crucial and somewhat mysterious roles in galaxy formation and evolution throughout cosmic history. James Webb has detected evidence of massive black holes containing millions or billions of solar masses in very early galaxies, much earlier in cosmic history than astronomers expected such cosmic monsters to exist. These gravitational giants help regulate star formation by heating gas throughout their host galaxies and preventing it from collapsing too rapidly into new stars, effectively controlling the pace of galactic evolution. The colours and shapes of early galaxies tell detailed stories about their formation histories that astronomers can read like cosmic genealogies written in light. Blue galaxies are actively forming new stars at rapid rates, their young stellar populations burning bright and hot with nuclear fires. Redder galaxies have more mature stellar populations dominated by older, cooler stars, suggesting they've completed most of their star formation and settled into galactic middle age. Irregular shapes often indicate recent mergers or ongoing gravitational interactions that are actively reshaping the galaxy's structure and stellar distribution. James Webb's observations show that galaxy formation continues today, though at a much slower and more stately pace than in the infant cosmos when mergers were violent and common and star formation rates were extreme. Even in our local cosmic neighbourhood, we can observe galaxies interacting, slowly merging and gradually evolving, demonstrating that the universe remains a dynamic, changing place where cosmic evolution continues its patient work of building ever larger and more complex structures. The cosmic web, the largest and most profound structure in the entire universe, emerges from James Webb's observations as a vast network of dark matter filaments connecting galaxies across billions of light-years of space like a three-dimensional spiderweb of invisible matter. This cosmic infrastructure provides the highways along which galaxies form and evolve, channeling matter from the sparse cosmic voids into the dense nodes where galaxy clusters form, like cosmic metropolises containing thousands of individual galaxies. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing thousands of galaxies held together by their mutual gravitational attraction and embedded in vast halos of dark matter that outweigh the visible matter by factors of 5 to 1. James Webb can observe these clusters at various stages of formation and evolution, watching as individual galaxies fall into the cluster's gravitational well and become permanent residents of these cosmic cities that stretch across millions of light years. The telescope's observations reveal that galaxy formation is not a smooth, gradual process, but involves periods of rapid growth punctuated by quieter phases of slow evolution and consolidation. During major merger events, galaxies can double or triple their mass in relatively short cosmic timescales, while during quiet periods they slowly accumulate matter from their surroundings and evolve more gradually through internal processes like ongoing star formation and stellar evolution. Environmental effects play crucial roles in galaxy evolution, with galaxies in dense cluster environments evolving very differently from isolated galaxies drifting alone in the cosmic voids. Cluster galaxies often have their star formation quenched by interactions with hot intergalactic gas and frequent encounters with neighbouring galaxies, while isolated galaxies can continue forming stars for much longer periods, sometimes maintaining active star formation for billions of years. Astronomers using Webb have uncovered that galaxy formation involves not just the accumulation of stars and gas, but also the development of complex internal structures that give each galaxy its unique character and appearance. Spiral arms, central bars, nuclear bulges, and other galactic features emerge through gravitational instabilities and interactions that operate over hundreds of millions of years. These structures help regulate star formation patterns and control the distribution of matter within each galaxy, creating the beautiful and diverse galactic forms we observe throughout the universe. The study of galaxy formation through James Webb's unique observations reveals the universe as a vast construction project. Operating according to physical laws we're still working to fully understand and appreciate, each galaxy represents the successful completion of a billion-year building project, a cosmic architectural achievement that required the precise coordination of gravity, gas dynamics, star formation, stellar evolution, black hole growth, and countless other physical processes all working together in perfect harmony. As we observe this cosmic construction project unfolding across billions of years through James Webb's time machine vision, we gain profound appreciation for the universe's remarkable ability to create beauty, order, and complexity from the simplest initial conditions imaginable. The same fundamental physical laws that govern atoms and molecules also operate on cosmic scales to build the profound structures that fill the universe with light, beauty, and the endless possibility of life emerging wherever conditions permit. Each galaxy James Webb observes represents billions of years of cosmic evolution, countless stellar lives lived and ended, and the gradual accumulation of the heavy elements necessary for rocky planets and biological complexity. These island universes scattered throughout space are the result of the cosmos organizing itself through gravity, time, and the patient, inexorable work of physical processes operating across scales that dwarf human comprehension and challenge our ability to truly grasp the magnitude of cosmic architecture. The study of galaxy formation through James Webb's unique observations connects us to the deepest and most fundamental questions about existence itself and our place within the cosmic story. How does the universe create order from chaos? How do simple physical laws operating over vast timescales give rise to complexity, beauty, and structure? How do we fit into this vast cosmic narrative of organization and evolution that began nearly 14 billion years ago and continues today? The telescope's revelations about galactic evolution also teach us about resilience and adaptation on cosmic scales. Galaxies survive collisions that would destroy any human-made structure, emerging from these encounters transformed but intact. They adapt to changing environments, adjusting their star formation rates and internal structure in response to external influences. They persist across billions of years, slowly evolving while maintaining their essential identity as gravitational communities of stars. In studying these cosmic cities through James Webb's eyes, we also gain new appreciation for our own galactic home, the Milky Way. Our galaxy is itself the product of billions of years of evolution, mergers, and gradual growth. The stars we see in our night sky are all members of this vast stellar community that stretches across 100,000 light-years of space and contains over 200 billion individual stars, each potentially hosting its own family of planets. The Milky Way's spiral structure, visible as a bright band across our night sky, represents the same type of galactic architecture that James Webb observes in distant galaxies throughout the universe. Our solar system resides in one of these spiral arms, about halfway between the galactic centre and edge, positioned in what astronomers sometimes call the galactic habitable zone, where conditions may be optimal for the development of life. James Webb's observations of galaxy formation also reveal the universe as a master recycler, where matter cycles between galaxies, stars, and the space between them in endless loops of cosmic renewal. Gas expelled by stellar winds and supernova explosions eventually falls back into galaxies to form new generations of stars. Elements forged in stellar cores are distributed throughout galaxies and eventually incorporated into new stellar systems and planetary families. This cosmic recycling process ensures that galaxies remain dynamic, living systems rather than static collections of old stars. Even primeval galaxies continue to form new stars from recycled material, maintaining their vitality across cosmic time. The elements that make up our bodies have likely been part of multiple stars and galaxies throughout cosmic history, connecting us to the universe's ongoing cycle of stellar death and rebirth. The patterns of galaxy formation that James Webb reveals also hint at the universe's ultimate fate and destiny. By studying how galaxies evolve over cosmic time, astronomers can project forward to understand how these structures will continue to change in the far future. The universe's expansion will eventually separate galaxy clusters, leaving each cluster as an isolated island in an increasingly empty cosmos. In the gentle darkness of space, surrounded by the light of billions of galaxies, each containing billions of stars, we contemplate our place in this profound cosmic architecture with wonder and humility. We are not detached observers standing outside the universe looking in, but active participants in its ongoing evolution. Conscious beings emerge from the same fundamental processes that built the galaxies scattered throughout space around us, like islands of light in an infinite ocean of darkness and possibility. Our own existence represents a remarkable convergence of cosmic processes: the formation of our galaxy, the birth of our sun from recycled stellar material, the condensation of our Earth from cosmic dust, and the emergence of life and consciousness from the patient work of evolution. We are the universe becoming aware of itself, matter organized in such a way that it can contemplate its own profound history and wonder at the beauty of its own architecture. Our cosmic journey now carries us towards some of the most awe-inspiringly beautiful sights in the entire universe. The nebulae that through Webb's eyes, astronomers have glimpsed in unique detail and stunning clarity. These cosmic clouds of gas and dust, illuminated by starlight and painted in colours that seem too profound to be real, represent the universe at its most artistic and creative. Cosmic masterpieces sculpted by the same physical forces that govern the dance of atoms and the motion of galaxies. Through James Webb's revolutionary infrared vision, we can see nebulae as never before in human history. The telescope's remarkable ability to peer through cosmic dust with perfect clarity reveals intricate structures and hidden details that were completely invisible to all previous instruments, no matter how sophisticated. What once appeared as simple, glowing clouds of luminous gas now reveal themselves as incredibly complex, three-dimensional sculptures carved by stellar winds, intense radiation, powerful magnetic fields, and the patient work of gravity operating over millions of years. These cosmic art galleries showcase the universe's remarkable ability to create beauty from the most fundamental physical processes. Each nebula represents a unique collaboration between matter and energy, gravity and radiation, creation and destruction, resulting in structures of such stunning beauty they challenge our capacity to fully appreciate their magnificence. The Crab Nebula, the spectacular remnant of a supernova explosion observed and carefully recorded by Chinese astronomers in 1054 AD, appears through James Webb's infrared eyes as an intricate tapestry of delicate filaments and glowing knots that stretch across several light-years of space. The massive explosion that created this nebula scattered precious heavy elements across vast distances, elements that will eventually become incorporated into new stars, new planets, and perhaps even new forms of life yet to be born. The shockwave from this ancient stellar explosion continues to expand even today, nearly 1,000 years later, heating the surrounding gas to millions of degrees and creating some of the most energetic phenomena in our galaxy. At the centre of this expanding shell of debris lies a pulsar, the ultra-dense core of the exploded star, now spinning 30 times per second and broadcasting beams of radiation across the cosmos like a lighthouse of incredible precision. The Ring Nebula showcases the gentle, graceful death of a sun-like star that exhausted its nuclear fuel after billions of years of steady burning. As the star ran out of hydrogen in its core, it began to shed its outer atmospheric layers in a series of elegant puffs and gentle stellar winds, creating concentric shells of glowing gas that appear like cosmic smoke rings drifting peacefully through the infinite darkness of space. James Webb reveals the incredible complexity of these nested shells, showing how even stellar death can create art on a cosmic scale. The colours in this dying star's expelled atmosphere tell stories of temperature and chemical composition. The central white dwarf star, the hot core left behind after the outer layers were expelled, ionizes the surrounding gas with its intense ultraviolet radiation. Different elements respond to this ionization by glowing in characteristic colours: hydrogen in deep red, oxygen in blue-green, nitrogen in red-orange, creating a palette of cosmic colours that rivals any earthly sunset. Perhaps most spectacular are the star-forming nebulae where new suns are currently being born, in processes we can observe unfolding in real time. The Eagle Nebula's famous pillars of creation appear through James Webb's infrared eyes as towering columns of dust and gas being actively sculpted by intense radiation from nearby young stars that have recently ignited their nuclear furnaces. These profound pillars stretch for multiple light years, each one a stellar nursery where gravity is patiently gathering material to form the next generation of stars. The infrared view reveals baby stars embedded within these dusty columns, protostars still gathering mass and slowly heating up as they approach the threshold of nuclear ignition. These stellar embryos are invisible to optical telescopes, hidden behind veils of cosmic dust, but James Webb's infrared vision penetrates these veils to show us stars in the very act of being born. The Horsehead Nebula, one of the most iconic and recognizable shapes in the night sky, reveals entirely new secrets through James Webb's penetrating infrared vision. What appears to optical telescopes as a dark silhouette against a bright background is actually a dense cloud of coal dust that blocks the light from stars behind it. But James Webb's infrared sensors can peer directly into this dark cloud, revealing the warm dust grains and embedded young stars hidden within, like treasures waiting to be discovered. This dark nebula represents a stellar nursery in its earlier stages, where gravity is just beginning to gather material together in preparation for future star formation. The intricate structure visible in infrared light shows how turbulence, magnetic fields, and radiation pressure create complex patterns within these apparently simple dark clouds. Planetary nebulae represent some of the most beautiful and geometrically perfect objects in the entire universe. Despite their name, These spectacular formations aren't actually related to planets at all, but are the glowing shells of gas expelled by dying stars similar to our Sun. James Webb reveals these nebulae in remarkable detail, showing complex structures, high-speed jets, and intricate knots of material that tell fascinating stories of stellar evolution and the final stages of stellar death. The Cat's Eye Nebula displays an incredibly complex structure of concentric shells, jets, and knots that suggest its central star expelled material in multiple episodes over thousands of years. Each shell represents a different phase in the star's death throes, creating a cosmic archaeological record of stellar demise preserved in glowing gas that will drift through space for hundreds of thousands of years. The colours in James Webb's nebula images correspond to different chemical elements and physical temperatures, creating a visual representation of the periodic table scattered across space. Hydrogen glows in characteristic wavelengths that appear red in processed images, while oxygen contributes blue-green hues and nitrogen adds red-orange tones. These colours allow astronomers to map the detailed chemical composition of nebulae and understand how different elements are distributed throughout space. Each nebula tells a unique and compelling story of stellar life and death, cosmic recycling, and the universe's ongoing creative processes. Some mark the birthplaces of stars, cosmic maternity wards where gravity assembles the next generation of suns. Others commemorate stellar deaths, memorializing the explosive ends of massive stars or the gentle passing of sun-like stars that have exhausted their nuclear fuel after billions of years of faithful service. Some nebulae show us stellar explosions that occurred thousands of years ago, expanding shells of debris that continue to race outward through space, heating and ionizing the surrounding interstellar medium. Others reveal the gentle shedding of stellar atmospheres as sun-like stars reach the peaceful end of their lives, returning their enriched material to space, where it will eventually become part of new stars and planets. The intricate structures within nebulae reveal the complex physics of stellar winds, radiation pressure, and magnetic fields operating on cosmic scales. Shock waves from stellar explosions create elaborate patterns as they sweep through the surrounding medium, compressing gas and triggering new rounds of star formation. Magnetic fields channel and shape the flow of ionized gas, creating the delicate filaments and twisted structures that make each nebula unique and beautiful. James Webb's images capture nebulae in multiple infrared wavelengths that reveal temperatures, densities, and chemical compositions completely invisible to human eyes. The telescope can distinguish between warm dust heated by nearby stars and cooler material in the outer regions, trace the distribution of different elements throughout the nebula structure, and map the three-dimensional architecture of these cosmic clouds with unique precision. Some nebulae appear to function as cosmic recycling centers, where the remains of dead stars mix with pristine interstellar material to create the raw ingredients for new stellar generations. These regions demonstrate the universe's remarkable ability to create beauty from destruction, to transform endings into beginnings, and to ensure that no cosmic material is ever truly wasted. The Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion, reveals through James Webb's vision an incredibly active stellar nursery where hundreds of new stars are currently forming. The nebula's gas glows with the light of hot young stars that have recently ignited, while cooler regions show the silhouettes of dense clouds where future stars are still gathering material. James Webb's infrared view penetrates the thick dust that obscures much of the Orion Nebula's structure, revealing a complex three-dimensional landscape of cavities, pillars, and flowing gas shaped by the radiation and winds from young massive stars. The telescope can observe individual protostars embedded within the nebula material, watching the star formation process unfold across this stellar nursery. The study of nebulae through James Webb's eyes reveals the universe as a master artist working with light, gas, and gravity to create sculptures of unimaginable beauty and complexity. Each nebula is unique, shaped by its particular history of stellar birth, life, and death, yet all share the common themes of transformation, renewal, and the eternal cycle of cosmic creation and destruction. The Rosette Nebula appears like a cosmic flower blooming in space, its petals formed by the radiation and stellar winds from hot young stars at its centre. The intricate structure reveals how star formation is a self-regulating process. The very stars being born help to sculpt and eventually disperse the material from which they formed. Emission nebulae glow with their own light, energized by ultraviolet radiation from hot young stars. These stellar nurseries appear in James Webb's images as vast regions of glowing gas painted in the characteristic colours of ionized hydrogen, oxygen, and other elements. The telescope's sensitivity allows it to detect the faintest wisps of gas and the most subtle colour variations. Reflection. Nebulae appear blue in optical light because they reflect and scatter starlight from nearby stars, but James Webb's infrared vision reveals the warm dust within these clouds. These nebulae often surround young stars, the leftover material from the star formation process that continues to glow with heat from the stellar birth. Dark nebulae, like the famous Horsehead, appear as dark silhouettes against brighter backgrounds. But James Webb's infrared sensors reveal these apparently empty regions as complex structures filled with cold dust and molecules, often harbouring the earlier stages of star formation, where gravity is just beginning to gather material together. Supernova remnants showcase the universe's most violent explosions frozen in time. These expanding shells of debris, moving at thousands of kilometers per second, create some of the most dramatic and beautiful structures in the cosmos. James Webb can trace the composition and temperature of these blast waves as they plough through the interstellar medium. The Veil Nebula, another supernova remnant, appears through James Webb's eyes as delicate lace-like filaments of gas heated to millions of degrees by the ancient stellar explosion. The intricate structure reveals how the blast wave interacts with the surrounding medium, creating regions of compression and rarefaction that highlight the complex physics of these cosmic catastrophes. As we drift through these cosmic art galleries, surrounded by some of the most beautiful sights in the universe, we gain new appreciation for the aesthetic dimension of cosmic processes. The universe doesn't just mindlessly follow physical laws. It creates beauty as a natural and inevitable consequence of those laws operating over space and time, matter and energy, interacting to produce forms of stunning elegance. These nebulae remind us that we are intimately connected to the cosmic processes that create beauty throughout the universe. The same stellar winds that sculpt nebulae once shaped the gas cloud that eventually collapsed to form our solar system. The same elements that glow in these distant clouds flow through our bodies, making our existence possible and connecting us to the cosmic cycles of creation and destruction. The heavy elements scattered by supernova explosions and stellar winds eventually find their way into new star systems, becoming incorporated into rocky planets where they can participate in the complex chemistry of life. The calcium in our bones, the iron in our blood, the carbon in our cells, all were once part of stars that died and returned their enriched material to space through the beautiful processes we observe in these cosmic clouds. James Webb's nebula observations also reveal the universe's remarkable efficiency at recycling material. Nothing is ever truly lost. Stellar death becomes the foundation for new stellar birth. Destruction becomes creation. Endings become beginnings. This cosmic recycling ensures that the universe continues to evolve and create new forms of beauty and complexity across cosmic time. In the gentle darkness of space, surrounded by these monuments to stellar life and death, we contemplate the universe's endless capacity for transformation and renewal. Each nebula represents both an ending and a beginning, a death that becomes the seed of new life, a reminder that beauty and meaning can emerge from even the most violent cosmic processes. The nebulae that James Webb reveals in such stunning detail serve as cosmic cathedrals where we can contemplate our place in the universe's ongoing story of creation. These clouds of gas and dust illuminated by starlight and shaped by physics, represent the universe's natural tendency to create beauty, complexity, and meaning from the simplest materials and the most fundamental forces. As we prepare to continue our journey through James Webb's cosmic revelations, we carry with us the memory of these beautiful nebulae and their lessons about transformation, renewal, and the universe's endless creativity. In their glowing gases and intricate structures, we see reflected the same processes that gave birth to our solar system, our planet, and ultimately to us. As our cosmic journey through James Webb's revelations draws to its gentle close, we find ourselves returning to this quiet moment, floating peacefully in space alongside humanity's greatest eye on the universe. We have travelled together through deep space and deep time, witnessing wonders that no human generation before us could have imagined, discoveries that reveal the universe to be far more profound, mysterious and beautiful than we ever dared to dream in our most ambitious scientific fantasies. We began our voyage 1 million miles from Earth, in the cold silence of space where James Webb keeps its eternal vigil at Lagrange Point 2. From that cosmic vantage point, we've journeyed to the very edge of the observable universe, looking back through billions of years of cosmic time to see galaxies as they existed when the cosmos was young and wild. We've witnessed the birth of stars in nebula nurseries larger than entire solar systems, analysed the chemical compositions of atmospheres surrounding distant worlds that might harbour life, and observed the slow, patient process by which the universe organised itself from nearly perfect simplicity into the profound structures that fill space with light, beauty, and infinite possibility. Through it all, one profound truth has emerged from every discovery, every image, every scientific revelation that James Webb has shared with us. We are not separate observers standing outside the cosmos we study. We are part of it, intimately and fundamentally connected to every process we've witnessed, every star we've seen born in stellar nurseries, every galaxy we've watched form from primordial gas clouds. The atoms in our bodies were literally forged in the nuclear furnaces of ancient stars that died billions of years ago. The elements flowing through our blood were scattered across space by supernova explosions that occurred when the universe was young. The very air we breathe connects us to the atmospheric processes that govern worlds throughout the cosmos. Consider for a moment the remarkable journey that brought you to this peaceful moment of rest and contemplation. The hydrogen in your body was created in the first few minutes after the Big Bang, when the universe was unimaginably hot and dense and filled with the primordial fire of creation itself. That ancient hydrogen eventually found its way into the molecular clouds we've observed tonight, where gravity patiently gathered it together with cosmic dust over millions of years to form new stars and the planets that orbit them. Some of the heavier elements that make up your physical being, the carbon that forms the backbone of every organic molecule in your cells, the oxygen that powers your cellular metabolism and allows you to extract energy from food, the iron that carries oxygen through your bloodstream, were created in the nuclear cores of massive stars that lived fast and died young in spectacular supernova explosions. These stellar giants burned through their nuclear fuel in just a few million years, then scattered their chemically enriched material across vast regions of space in death throes so violent they briefly outshone entire galaxies containing billions of stars. The calcium that gives strength to your bones was forged in the cores of intermediate mass stars that took hundreds of millions of years to complete their full life cycles. The phosphorus that forms the backbone of your DNA was created in the explosive final moments of stellar death, when nuclear fusion could no longer sustain the star against gravitational collapse. Even the trace elements that your body needs to function properly, zinc, copper, selenium, and dozens of others, were manufactured in stellar furnaces and distributed through space by stellar winds and cosmic explosions of incredible violence and beauty. This remarkable fact means that you are literally made of cosmic dust from dying stars, composed of atoms that have travelled through space for billions of years, cycling through multiple generations of stars, planets, asteroid belts, comet nuclei, and perhaps even other forms of life. You're a temporary but meaningful arrangement of cosmic material that has gained consciousness and the miraculous ability to contemplate its own origins and place in the vast scheme of existence. The incredible journey these atoms took to become you spans the entire history of the universe, from the Big Bang to this present moment. They were present at the creation of space and time itself, witnesses to the formation of the first hydrogen and helium nuclei, participants in the assembly of the first galaxies and the birth of the first stars. They've been part of rocky planets and gaseous nebulae, asteroid belts and comet nuclei, ocean water and atmospheric gases, living organisms and geological formations. Now they're part of you, organised in such a miraculous way that they can think and feel and wonder about their own cosmic heritage. James Webb's discoveries remind us that this cosmic connectivity extends far beyond just the atoms in our physical bodies. The fundamental physical laws that govern stellar formation and galactic evolution are precisely the same laws that govern the biochemistry of life and the electrical firing of neurons in our brains. The electromagnetic radiation that illuminates nebulae and powers stellar fusion through nuclear processes also enables the photosynthesis that feeds all life on Earth and forms the foundation of every food web on our planet. The gravitational forces that shape galaxies over billions of years and guide the formation of planetary systems also keep our feet planted firmly on Earth's surface and maintain our planet in the stable orbit around the Sun that makes life possible. The nuclear processes that power distant stars across the cosmos also warm our world and drive the weather patterns, ocean currents, and atmospheric circulation that sustain Earth's remarkably diverse biosphere. This deep interconnectedness suggests that consciousness itself might be a natural and perhaps inevitable consequence of cosmic evolution, an outcome of the universe's fundamental tendency to create ever greater complexity, organisation, and beauty. The same processes that assembled galaxies from primordial gas clouds also assembled our brains from cosmic elements, creating biological structures capable of contemplating the very cosmic processes that created them in an endless loop of cosmic self-awareness. In looking out at the cosmos through James Webb's unique infrared eyes, we are literally the universe looking at itself with wonder and appreciation. We are matter organised in such a remarkable way that it has become aware of its own existence and can marvel at its own beauty, complexity, and profound creativity. This represents perhaps the most remarkable achievement in cosmic evolution. The universe has become conscious of itself through the emergence of thinking, feeling beings like ourselves. The discoveries we've shared tonight also remind us of our responsibilities as conscious participants in the ongoing cosmic story. We are the universe's way of understanding itself, and with that understanding comes a profound responsibility to preserve and protect the conditions that allowed consciousness to emerge on our planet. Earth is the only known harbour for life and consciousness in our cosmic neighbourhood, making it precious beyond any possible measure or valuation. James Webb's revelations about the abundance of potentially habitable worlds throughout the universe fill us with hope and wonder that life and consciousness might not be rare cosmic accidents, but natural outcomes of cosmic evolution operating under the right conditions. If this proves to be true, then consciousness might be emerging throughout the cosmos at this very moment, creating countless other perspectives from which the universe can contemplate its own magnificence and meaning. The telescope's ongoing observations continue to expand our understanding of our place in the cosmic story with each new discovery. Each new image, each new spectrum, each new revelation adds another chapter to the growing narrative of cosmic evolution, revealing new connections between distant astronomical phenomena and our own existence here on Earth. The universe continues to surprise us, challenge our assumptions, and expand our sense of wonder and appreciation for the beauty of existence. The James Webb Space Telescope itself represents humanity at our very best. Our insatiable curiosity about the cosmos, our remarkable ingenuity in solving technical challenges, our deep desire to understand our place in the universe, and our ability to work together across national and cultural boundaries to achieve goals that no single person or nation could accomplish alone. This profound instrument embodies our species' greatest aspirations and our most noble impulses. Every image James Webb captures, every spectrum it analyzes, every discovery it makes represents the collective effort of thousands of scientists, engineers, technicians, and dreamers who dedicated their lives to making this cosmic vision possible. The telescope is a testament to human persistence, creativity, and the power of scientific collaboration to reveal truths about the universe that transform our understanding of existence itself. As we've journeyed together through James Webb's discoveries, we've also journeyed through our own cosmic heritage. The early galaxies we observed contain the stellar ancestors that created the elements in our bodies. The stellar nurseries we explored show us processes similar to those that formed our sun and solar system. The exoplanets we studied remind us that worlds like Earth might be common throughout the cosmos, each one a potential harbour for life and consciousness. The nebulae we've admired represent the cosmic recycling centres, where the materials of our bodies will eventually return, continuing their eternal journey through space and time. In these glowing clouds of gas and dust, we see both our cosmic origin and our ultimate destination, the endless cycle of stellar birth, life, death, and rebirth that connects all matter in the universe. As you prepare to drift off to sleep tonight, carry with you the profound knowledge that you are part of something infinitely larger and more beautiful than your daily concerns and worries. You are a temporary but meaningful arrangement of ancient atoms that has gained the miraculous ability to contemplate the cosmos from which you emerged. Your thoughts and dreams tonight are cosmic events, matter thinking about itself across the vast scales of space and time. The stars you might glimpse through your window before sleep are your stellar relatives, fellow travellers in the cosmic journey that began nearly 14 billion years ago. The galaxies James Webb observes in the distant universe are your extended cosmic family, part of the same vast web of matter and energy that gave rise to you. The nebulae we've explored tonight are both your birthplace and your eventual destination, the cosmic recycling centres where your atoms will eventually return to continue their eternal journey through the cosmos. Rest peacefully in the knowledge that you are exactly where you're supposed to be in this vast unfolding cosmic story. You are the universe becoming conscious of itself, matter, learning to think and feel and wonder about its own existence. You are cosmic dust from dying stars that has learned to dream, cosmic material organised in such a miraculous way that it can experience beauty, love, wonder, and the profound peace that comes from understanding our place in the profound cosmos. The universe has spent nearly 14 billion years preparing for this moment, for you to exist, to think these thoughts, to feel this connection to the cosmos. Every galaxy that formed, every star that ignited, every planet that coalesced, every molecule that evolved was part of the cosmic chain that led to you lying here tonight, contemplating your place among the stars. Tomorrow will bring new discoveries from James Webb, new images that will expand our understanding and deepen our sense of wonder. The telescope continues its patient work, capturing light that has travelled for billions of years to reach us, revealing new chapters in the cosmic story that we're only beginning to read and understand. But tonight, in this quiet moment, you can rest in the knowledge that you are part of the greatest story ever told, the story of how the universe evolved from a hot, dense beginning into the profound cosmos we see today, filled with galaxies and stars, planets and nebulae, and somehow, amazingly, with conscious beings capable of appreciating its beauty. If this gentle journey through space and time has brought you comfort and wonder, if these revelations from the edge of the observable universe have helped quiet the concerns of the day and filled you with appreciation for the beauty of existence, consider sharing this cosmic perspective with others who might also find peace in understanding their connection to the stars and galaxies that surround us. The story continues in you, through you, because of you. Sleep well among the stars, knowing that you carry within yourself the wisdom and beauty of the entire universe. Dream of distant galaxies and newborn stars, of nebulae painted in impossible colours and worlds that might harbour life among distant suns. The cosmos is vast beyond measure, ancient beyond comprehension, and beautiful beyond words, and you are part of it all, forever and always, world without end. Sleep peacefully, cosmic traveller. Sleep well in the gentle embrace of the infinite universe that dreamed you into existence,